Hello, my name is Krishna Hanumantu. I work in Chennai Mathematical Institute, and in this 8-week course we are going to learn basics of rings and fields. Course title is Introduction to Rings and Fields. So, rings and fields are algebraic objects which have some operations on them satisfying certain properties. So, this is a course that one does after learning some basic group theory and some linear algebra. So, this is I am going to keep this as self-contained as possible, and the course will focus a lot on examples and problems. I will introduce some definitions and do important theorems, but at the same time I will talk about various examples and solve problems in my videos. So, in today's video I will give some examples of rings and then define them and study properties. So, roughly the plan for the course is around half the time, about 4 weeks we will do rings, 4 to 5 weeks, and the remaining time we will do fields. Fields are just special cases of rings, they are rings with certain additional properties. So, after studying ring theory we will focus on fields for the last part of the course. So, let us start today with a general introduction to rings. So, I am going to start with basic examples before I give you the formal definition of a ring. Okay. So, you all know what a group is. A group is a set with an operation on it which has certain properties, which are the properties are there is an identity element, every element has an inverse, the operation is associative. So, a ring is something which has two operations. It's usually we call these operations addition and multiplication. With respect to addition, the ring is supposed to be an abelian group. With multiplication, it need not be a group. So, before I talk more about the definition, let me start with some examples. So, we will start with some examples of rings. Okay, so, the first example that I want to discuss, which is in some sense the most important ring, is this set of integers. So, Z always when I write Z in this way, I always mean the set of all integers. We know this as a group under addition, but in fact it is also an example of what we want to consider as rings. So, here there are two operations. So, they are the usual addition and multiplication, right. So, plus is the addition of integers, and let us denote multiplication by star cross. So, multiplication is the usual multiplication of integers. So, with respect to these two, what are the properties of Z? So, Z comma plus, so that means the set of integers with addition is an abelian group. Okay. So, this is something that you would have seen in a course on group theory, meaning there is this operation is closed on the set of integers, meaning you add two integers, you get another integer. There is a identity element, namely 0. 0 is a identity element for the addition, meaning if you add 0 to any element, you get 0. There is also inverse for every element. Every element has an inverse that if you add the 2, you get 0. For example, inverse of 3 is minus 3, inverse of minus 10 is 10. Similarly, the addition is associative. So, you can add 3 integers in either of the two natural ways. So, this is an abelian group. So, this we know. What about the properties of integers under multiplication? So, Z cross. So, clearly this is not a group, right. This is also something you would be familiar with. This is not a group because it is certainly closed, but there are no inverses here. There is no identity also, because 1 would be the most obvious candidate for the identity element, because 2 times 1 is 2, but 0 does not have any inverse. No number when you multiply by 0 you get 1. Similarly, you do not have inverses. For example, there is no number that you multiply 2 with to get 1. Okay. So, it is not a group, but for a ring we do not care whether multiplication is a group or not. So, this is not necessary for a ring. So, this is the first important point. So, we do not need the set to be a group under addition, under multiplication rather I should say. So, it is not a group under multiplication. Okay. So, some other examples. So, Z is our typical example of a group. So, let us look at the next example. So, these are also familiar to you. So, the set of rational numbers, Q always stands for set of rational numbers. Is this a group? Is this a ring? Let us see. So, clearly it has 2 operations, it has plus and multiplication. Q under addition is an abelian group, right. So, if you add 2 rational numbers, you get a rational number, there is a 0 element, every rational number has an inverse, it is associative. And remember also I am noticing that it is an abelian group. If you have 2 rational numbers, you can add them in either order and you get the same answer. Again, just like with the case of integers, Q with multiplication is not a group. However, it is actually better than Z with multiplication, because if you remove 0 from Q and consider multiplication, it is a group, right. So, this is something that you would have seen in a course on group theory. Non-zero rational numbers with multiplication is a group under, it is called multiplicative group of rational numbers, non-zero rational numbers, because here one is identity element, every rational number has an inverse, and it is certainly associative, and in fact it is even an abelian group. Okay. So, I will just do 1 or 2 more examples. So, similarly, so this is not really a new example. So, similarly we have the real numbers. So, set of real numbers, these are, I am introducing these because also these are important sets for us that provide very important examples for rings and fields that we talk about in this course. So, C stands for set of all complex numbers. Okay. So, just like Q, these have also 2 operations, namely addition and multiplication. Under addition they are abelian groups, and once you remove 0 they become abelian groups under multiplication. With 0 certainly you cannot expect them to be groups under multiplication, because 0 does not have an inverse. Okay. So, now I will just do one more example to not maybe so obvious, but we want to discuss this in more detail later on. So, consider, so I will write a symbol here and I will explain. Okay. So, let us look at Z square bracket I, where I is a square root of, so it is a complex square root of so as usual we denote I, we denote the complex square roots of I by minus 1 by I and minus I. So, square root of, okay, so I stands for square root of minus 1. So, consider this set Z I. What is this set? So, I am defining this set to be all elements of the form A plus I B, where A and B are integers. So, that Z is playing a role here. Okay. So, Z I stands for A plus I B, where A, B are elements of Z. For example, 1 is an element of Z I, minus 1, in fact any n is an element of Z I, right, for all n in Z, because it is n plus I times 0. Similarly, 3 plus 2 I is an element of Z I and so on. So, you understand. So, you have these elements of Zi. So, it's we understand this is a subset of complex numbers, right. So, this is a subset of complex numbers because a plus ib is a complex number. Only we are restricting a and b to be integers. In general, a and b are any real numbers, that way you get any complex number. Now, we want to only look at integers, a and b are integers. So, it is a subset. I want to think of this as a ring later on. So, we can add two elements of Zi, right. So, there is an obvious addition, just like you add them as if they are complex numbers, right. So, if you have c plus id and a plus ib, you add them you get a plus c. You first add the real parts, so to speak, and then you will add the imaginary parts. So, a plus c plus b plus d, right. So, b plus d. So, now if this is in Zi and this is also in Zi, that means what? A and b are integers by definition, c and d are integers by definition. So, a plus c is an integer, b plus d is an integer. So, this is also in Zi, right. So, in other words, what we have just showed is Zi is closed under addition. So, if you add two elements of Zi, you get another element of Zi. In fact, you can check quickly that it is easy to check. I will leave this for you to check in detail. Easy to verify that Zi is in fact an abelian group under addition. So, if you remember your group theory, what I am really saying is that in fact it is a subgroup of the complex numbers with addition. It is a subgroup of the complex numbers under addition. See, this is easy to check that it is an abelian group because there is the 0 element. 0 element is of the form a plus bi, right, where a and b are integers. It is 0 plus I times 0. Every element has an inverse. A plus ib has inverse minus a minus ib, that is also in Zi, and certainly it is associative because addition of complex numbers is associative and it is closed, we checked. So, it is an abelian group. So, that is, remember, one of the properties we are looking for in a ring. So, it is a group, that is old news. So, it is a group. So, this is the first property. We also need another thing for a ring. We need multiplication on the set that we want to consider as a ring. So, there is multiplication on complex numbers. We need to still verify that Zi is closed under multiplication. So, let us choose two elements of Zi. Let us say a plus ib, c plus id are inside Zi. Let me remind you, that means a and b are integers, c and I are integers. If you multiply them, just thinking them as a complex numbers, what would you get? What is a plus ib times c plus id? A plus ib times c plus id is, this is the usual multiplication, you will get ac minus bd, right, because I squared is minus 1. So, that will be the real part, plus I times ad plus bc. Now, a b c d are integers. So, ac minus bd is an integer, ad plus bc is an integer. So, this is also in Zi. So, first point I want to note is Zi is closed under multiplication. We proved that here. So, it is closed under multiplication, which is an important property for a ring. There is a multiplication on the set and it has identity. One is in Zi, and it is associative because this follows directly because the complex number multiplication is associative. So, and it has some other properties that I will talk about once I discuss the formal definition of a ring. Okay. So, now let me just do one more example where things do not go well. So, this is the second property. So, I will label it as 2. Final example I want to talk about before giving you the definition of a ring. So, this is example 4. Let us look at similar to Z I, let us look at Z, let us say 1 by 2. Z 1 by 2, I will just take this. So, actually this is not what I am writing is not correct. So, let me just define a new symbol for this, let us say A. Okay. So, A is I am just replacing I by 1 by 2 in the earlier example. So, here we replace I by 1 by 2. Remember earlier we looked at A plus IB where A and B are integers. Here I am taking A plus B times 1 by 2 where A and B are integers. Okay. So, here if you multiply two things here, for example 1 by 2 is in A, right, because that is 0 plus 1 times 1 by 2, but 1 by 2 times 1 by 2 which is 1 by 4 is not in A. So, one can check that 1 by 4 cannot be written as, so this is an exercise for you, it is not a difficult exercise, 1 by 4 cannot be as A plus B by 2 for some integers A and B. You write it like this and you clear denominators and check that there is a contradiction. So, that means what I want to highlight here is that A is not closed under multiplication. So, this fails one of the important properties for a ring that we will define now. Okay. So, I am just trying to through these examples indicate to you that being closed under multiplication is a condition that one has to check. In general it does not hold. So, now let us go ahead and define what a ring is. So, we can talk more talk about more examples and properties of them. So, this course is about rings. Okay. So, this is the most important example for us. So, a ring, we denote rings by symbols R. A ring R is a set with two operations. So, I will write the full definition here. I have already indicated to you what the properties should be through these examples. So, you will see that they will appear here. A ring R is a set with two operations. So, or binary operations as they are called, denoted by plus and times. So, okay, this is these are called addition and multiplication. Okay. So, I want to emphasize also that it is just a convenient way of calling them addition and multiplication. It is not always the addition that we have learned in school, it is not addition of numbers or multiplication of numbers, it is an abstract operation. Okay. So, it is just convenient to call them addition and multiplication. Satisfying, so it has two operations that must satisfy the following properties. What are the properties that these two operations must satisfy? So, as I have already, these properties are axioms. Okay. So, I will write that here. properties or axioms. So, these are axioms of rings. Okay. So, it is a set with two operations denoted by plus and times called addition and multiplication, satisfying the following properties or axioms. First one is that R with addition is an abelian group. Okay. So, R with addition is an abelian group, this I have mentioned here before. If you just forget about multiplication, only look at addition, then it is just our familiar abelian group. So, with addition it must be an abelian group. Multiplication need not be with multiplication R need not be a group as we discussed, but it must still satisfy some conditions. What are they? Multiplication is commutative. So, I will describe what this is after writing this. Commutative is another word for abelianness. So, what I am saying is that if you multiply two elements of R, so let us say A and B are, so this I will write here. So, I will just make a box here and write. So, if A and B are in R, so multiplication is usually denoted by A dot B or just AB. For once we start writing more, we will write AB. So, this is also A times B. So, this must equal BA. So, remember abelian groups are what we call commutative groups. Commutativity is just another word for abelianness. So, no matter how you multiply the two elements, you get the same answer. AB is same as BA. So, multiplication must be commutative. Remember all the examples that we looked at, multiplication was commutative because all the examples we looked at were subsets of complex numbers where multiplication is commutative. We also need multiplication to be associative, which is a familiar property to you. A, B, C, if you have two elements, you can multiply them by grouping A and B first or grouping B and C first. So, either way you get the same answer. So, as associative, it contains an identity element denoted by 1. So, again it is convention to denote multiplicative identity just by 1, because in all the examples that we know 1 is the identity element, usual number 1 is the identity element. So, it contains an identity element and actually that is all. So, multiplication is commutative, associative, contains an identity element. So, you remember that I have not written the one of the properties for a group, namely I did not insist on existence of an inverse. So, I do not need an inverse. Multiplication is not a group operation on the set R, it has all the other properties. It is a binary operation, so it is closed by definition, it is associative, it contains identity element, and actually it has a property that now in general groups need not have, namely that it is commutative, but I am not asking for inverses. And the third property is very important. Anytime you have two operations on a set, you want these two operations to be well behaved with respect to each other, they should not be completely independent of each other. So, I will say that plus and times distribute. So, let me write distribute. So, this is the usual distributive property of integers or real numbers or complex numbers. What is this? For all A, B, C in R, A plus B times C. See, remember I have already indicated to you that when I multiply I do not put any symbol between the two elements, I just write A B to denote the multiplication of A and B. When I am adding I write A plus B. Okay, so, A plus B bracket C means you add A and B first, whatever the ring element is you multiply by C, that must equal AC plus BC. That means you first multiply A and C, similarly multiply B and C and add the results. So, AC plus BC must be same as A plus B times C. See, this is a property that is obvious for integers and real numbers and rational numbers, complex numbers that you have seen, right. But it is something that we must demand in a ring. It is possible that we can construct operations which have all the properties, but not the distributive property. So, we need to insist specifically on this property. So, this is a very natural and obvious property in the sets that we are used to, but it is not guaranteed to be true always. So, we need to insist on it. So, these are properties of a ring. So, this is the important example, important definition for the whole course. So, a ring is a set with two operations denoted plus and times that have the properties. With addition, it is just abelian group. Multiplication is almost a group except for one property, and plus and times have are well behaved in the sense that they satisfy distributive property. A plus B times C is same as AC plus BC. So, I want to now revisit the examples that I did in the beginning of the video, and now say that Z, Q, R, C, Zi are rings. So, now you might want to go back to the video, see it from the beginning, the first part of it when I discuss these examples. In all these examples, there are two operations. You can add two integers, you can multiply two integers. You can add two rational numbers, you can multiply two rational numbers. You can add two real numbers, you can multiply. Similarly, you can add complex numbers, you can multiply complex numbers. In fact, Z, Q, R are all subsets of C. So, once you know that there is addition and multiplication on C, these sets inherit them. However, you have to check that these sets are closed under that operation. For example, you add two integers, you get another integer. You add two rational numbers, you get a rational number. You add two real numbers, you get a real number. You add two elements of Zi, you get another element of Zi. Similarly, you multiply two elements of Zi, you get another element of Zi. Similarly, for Z, Q, R and C. And with addition, these are all abelian groups. I have asserted it, it is not difficult to check that. And with multiplication, they are not necessarily groups, but they have the property that they are commutative, they are associative, they contain identity element. In each of these cases, one is identity element, and the new property that one can check easily is that distributivity. So, distributive property holds for C. So, it also holds for the other sets above. Why is that? Remember, Z, Q, R, Zi are all subsets of C. So, in fact, between them there are these following inclusions. So, you have Z inside Zi, inside C, right. Z is certainly contained in Zi. You also have the inclusion Z contained in Q, contained in R, contained in C. Remember, Zi is not contained in R. So, we have these two inclusions. So, if the distributive property holds for elements of C, it holds for all these subsets. So, the final definition I want to give in this video, and that will allow me to talk about these things here as subrings of C, is the definition of a subring. So, once you have a subring, so if you recall, we have a notion of subgroups of a group. So, what is a subgroup? You start with a group G, and a subgroup is just a subset which by itself is a group. So, it has under the same operation that the ambient set group has, it is a group. So, it is closed under that, it has identity, it has inverses, and it is associative. So, similarly, let R be a ring, a subset S of R. So, we start with a subset is a subring. So, it is a subring. So, it is a sub object, just like subgroups are sub objects of groups. So, it is a subring if it is closed under addition and multiplication, and it is a so it is closed under plus times, it is a subgroup under of so it is closed under addition, but more than that it must be a subgroup of the additive group of R, and finally if it contains 1. So, the multiplicative identity. So, the subring is supposed to contain multiplicative identity. So, a subring is a subset if it is closed under addition and multiplication, it is a subgroup of the additive group of R and it contains 1. Okay. So, finally, I will end the video by saying that Z, Q, R, Z I are subrings of C, right. So, because C is a ring to begin with and these 4 sets are closed under multiplication and addition, they do form subgroups under addition, they contain 1. So, they are all subrings of C. So, I will end the video here, and in the next video we will look at more examples of rings and we will start looking at properties of rings. Thank you.